Hello and welcome to comp452 computer architecture. So we are going to continue our discussion, and we now want to design the main control unit. So before we start designing the main control unit, I would like to show you the complete data path and various control signals along with the ALU controller that we uh, designed in the previous part of the lecture. Okay, and I will also show you something that I did not discuss earlier, and I'll discuss it now because that was something that I completely forgot while we were talking about the data path. So let's begin. Okay, so this is the data path. Let me make it a little smaller so that we are able to see the whole thing. Yeah. Okay, this is our data path. Now in this data path, the blue lines, they are control signals, and there are a total of 9 such lines here. Actually, this ALU op are 2 lines, ALU op 1 and ALU op 0. Sorry, this ALU op, this is not 1 but 2 lines. Okay, now this is a mux that I forgot to mention while we were discussing the data path or while we were developing the data path. Now what is this mux doing? Look, there are 2 inputs. This is a 2 to 1 mux. This is a 2 to 1 5-bit wide mux. 2 to 1 5-bit wide mux. The 0 input of this mux gets bit 16 to 20 of instruction, and this bit 16 to 20 of instruction is where the RT field of the instruction is located, and the one input of this mux gets bit 11 to 15 of instruction where RD is located, destination register. Why do we need this mux? This is very important. You know, the destination register, let's take the case of R-type instructions. Okay, in R-type instructions, the format is instruction, then destination register RD, then first source register RS, then second source register RT. Okay, But for I type instruction, and I am now talking about load word instruction, the destination register is RT, and we have offset and then RS. Why don't we have RD here? The reason is that the RD field is located in, let me clarify, RD number is located in bits 11 to 15 of instruction. Okay, but in I type instructions, bit 11 to 15 are part of the offset. In I type instructions, in load word and store word and other I type instructions, bits 11 to 15 are part of the offset and therefore cannot carry or cannot contain the destination register number. The destination register number. Okay. Therefore, for load word instruction, LW means load word instruction, the destination, it's not destination, it's destination, sorry about that. The destination register number goes in RT field of instruction. Actually, this RT field of instruction is also the destination register number for add I, subtract I, AND I, OR I, NOR I, SLTI, and all the I variants of R type instructions. Okay, so it is the use of this multiplexer. This multiplexer is not just limited to load word instructions, but all I variants of R type instructions, they also use this multiplexer. Okay, so it means that if our instruction is a load word instruction, then we need to route the destination register number from bit 16 to 20. Bit 16 to 20. Okay, this is when we have load word or other I type instructions where some value has to be stored in a register. But if it's an R type instruction, then the destination register comes from bit 11 to 15 of the instruction. So this is the reason that we need a multiplexer here, and since this is a 2 to 1 5-bit wide multiplexer, it will have only one select line, and that select line is we call it REGDSD, register destination. Okay, so I forgot to discuss this mux when we were discussing the data path in lecture 8b. In lecture 8b, this mux is when it's an R-type instruction. When the processor is executing an R-type instruction, this yellow line it goes to the output into the write register input of the register file, and when it's an I-type instruction like load word or add I, subtract I, and I, or I, nor I, SLTI, then this green line that contains the destination register number, which is written into write register field of the register file. Okay, so now we have clarified this thing, so let's quickly talk about other multiplexer select lines. So the next multiplexer select lines is ELU source. This ELU source. Okay, now you can see that this ELU source line, it will be 0 for all R-type instructions. It will be 0 for all R-type instructions, and it will be 1 for I-type instructions such as load word, store word, add I, and I, or I. For all these instructions, the ALU source select line will be 1. Okay, so ALU source will be 0 for all R-type instructions, and it will be 1 for all I-type instructions. There is one exception here, and I should tell you that exception. There is one case in which the instruction is I-type but ALU source is 0, and that is when processor is executing branch if equal instruction. Branch if equal instruction. That is the R-type that is an I-type instruction, but ALU source is set to 0. Why? Because branch if equal has to perform subtraction to test the equality of two registers, and one of the register is RS, whose value comes from the read register 1 output, and the other register is RT, whose value comes from read data 2 output. So this mux must be 0 when branch if equal instruction is executing. Okay, so that is the only case. I should actually clarify that in the set of instructions that we are implementing, that is the only case. Branch if equal instruction is the only case in which the instruction being executed is I-type, but ALU source is set to 0. Otherwise, ALU source is 0 for R-type instructions. Okay, so next we come to which mux? PC source mux. This PC source mux, PCSRC. Now this mux is 0 if it's not a branch instruction. If it is not a branch instruction, then PC source is 0. And PC source is 1. PC source is 1 if the instruction is a branch instruction and branch is taken. Okay, so PC source is 1 if instruction is branch if equal and the branch is taken, and the branch is taken, which means that the two registers have same value in it. Otherwise it's 0. Okay, all right. Now let's talk about this mem to reg. This mem to reg signal is 1 when load word instruction is executing, when load word instruction is executing, and mem to reg is, this mem to reg signal is 0 when R type instructions are executing or I variant of R type instructions are executing. For example, add I, subtract I, and I, or I. When these instructions are executing, then this mem to reg is 0, and it is 0 for all R type instructions. Okay, because when mem to reg has to be 0 when the result produced by ALU has to go to the has to go to a destination register. For example, we perform an add operation, so, and we want to store the result of add operation in a register, so mem to reg must be set to 0 so that the result produced by ALU can go to the this write data input of register file. Okay, so we have discussed these multiplexer select lines. Now we have a few more lines. Reg write. When is reg write 1? Reg write is 1 for all R type instructions, and it is 1 for load word instruction, because in load word instruction something is read from memory, a value is read from memory and written to a register. Okay, so that's why reg write has to be 1 for load word, and it must be 1 for all R type instructions. Okay, let's talk about mem write. Mem write will be 1 for store word instructions, and mem read will be 1 for load word instructions. Load word instruction. Now we have completed our discussion of all control signals. Well, obviously we talked about ALU op in the previous part of this lecture, so we already know that these 2 bits are controlled by the main controller, and if these 2 bits are 0 0, then we program ALU controller to we program the main ALU to do addition operation. If it's 1 0, then subtraction, and if it's no, I'm sorry, when it's let me check again. I don't want to tell you something which is not correct. Let's see. Yeah, when ALU op 1 and ALU op 0 are both 0, then we do add operation. If ALU op 0 is 1, then we do subtract operation, and when ALU op 1 is 1, then we pass on the function code, then ALU controller examines the function code to determine what operation needs to be performed. Okay. All right. So now, what will be the outputs of our main controller? It is so obvious that all these blue lines, REG DST, ALU source, these two lines ALU op, PC source, memwrite, memread, this is memread, and this mem2reg. These are the outputs of our main controller. Okay, so our main controller has 9 outputs. It has 9 outputs. And what is the input of the main controller? What is the input of the main controller? Now, input of the main controller obviously are the 6 bits of opcode. Input of the main controller are the 6 bits of the opcode. Do we need any other inputs besides those 6 opcode bits? Do we? Actually, we don't. That's all we need. For our purposes, for the instructions that we are implementing, those are the only 6 inputs that we need in our ALU controller. Okay, so now let's go on to the next page and let's start developing our truth table. Okay, so how many inputs are there? Instruction opcode, let's write it like this. Op5, op4, op3, op2, op1 and op0. These are the 6 inputs. Okay, what are the outputs? We have, let's use blue color for the outputs. We have reg DST. We have memread. Actually, we have memread, I'm just writing MRD, memRD. Then we have mem2reg, then we have 2 bits of ALU op, these are actually 2 bits. Then we have memwrite, memwr, memwrite. Then we have actually, I have used too much space here. I'm actually, I'm going to erase everything because it's not going to work like this. I need to be more conservative in using the space. So I'll call, black color. So this is bit 5 of opcode. This is bit 4 of opcode. This is bit 3 of opcode, bit 2, bit 1 and bit 0 of opcode. Okay. Then I have reg dst that I want to write in blue color. Reg dst. Then I have memread. Then I have mem2reg, mem2reg, and then I have ALU op. These are 2 bits. Then I have memwrite, memwr, memwrite. Then I have ALU source, and then I have regwrite. Okay, now I have left this space here, and this is where I will introduce another output, which is the branch BR. Remember, let's go back here. I said this PC source is going to be one of the outputs of main controller. Actually, this PC source is not a direct output of the main controller. Main controller, if I think in one of the previous lectures I showed you that there is an AND gate, and one of the inputs of that AND gate is a signal coming from main controller, and the other input of that AND gate is coming from zero output of the ALU, this zero output of the ALU. Maybe I can draw it like this. No, that's not a good way to do it. Like this is better. This. Okay. So PC source is not a direct output of main controller. The direct output of main controller is branch signal, and this branch signal is one when the instruction is branch if equal. And if the output of the ALU, if the zero output of the ALU becomes asserted, which means that subtraction resulted in zero result, then this signal also becomes 1, and when both of these become 1, this output of the AND gate becomes 1, and it means that the branch is taken, and we route or we pass this value into the program counter so that execution can begin from here. Okay, so so this is that branch signal. It comes from the main controller when the instruction being executed is branch if equal. Okay, so now let's see what values should go into these columns. Okay, now if opcode bits are all zeros, then it's an R-type instruction. We know that. Then it's an R-type instruction. Okay, in R-type instruction, what will be the values of various signals? So we have an R-type instruction. So what will be the value of regdst? What will be the value of regdst? It's an R-type instruction. So in R-type instruction, the destination register number, the destination register number will come from bit 11 to 15, which is the yellow line. So it means REG should be 1. So let's come here and let's write here that REG would be 1. It's not a branch instruction, so BR will be 0. We do not want to read any memory, it will be 0. Mem to reg, now this is important, mem to reg, let's look here. This is mem to reg multiplexer. Oh, I'm sorry. No, I don't want to cast anything. Okay, this mem to reg, what will be the value of mem to reg for R type instructions? Obviously, it's going to be 0 because we want the result output of the ALU to pass through this multiplexer. So it has to be 0. So let's write 0 here. What would be ALU op? What would be ALU op? You know, for R type instructions, ALU op 1 is 1 and ALU op 0 is do not care. So 1 and do not care. Okay, what will be mem write? Mem write will be 0. We do not want to write any memory. What will be ALU source? Let's look here. This is the ALU source multiplexer. So obviously for R type instructions we have to have two register values sent to the main ALU. So ALU source must be 0. Let's come here and let's write ALU source 0. And what would be reg write? Let's see here. This is reg write. Reg write has to be 1 for all R type instructions. So reg write has to be 1 for all R type instructions. So we have basically covered all R type instructions with this one single line. All R type instructions. Okay. It includes AND, OR, NOR, SLT, add, subtract. Okay. Good. We are done. But now we want to talk about what other instructions we want to execute. We want to execute load word, we want to execute store word, and we want to execute branch if equal. Okay, now what is the opcode of load word instruction? It is 1001111. 1 triple, actually I think I should use green color. 1001111. This is load word instruction. Okay. Now let's see what should be the values of these blue signals for load word instructions. So let's go back. So in load word instructions, actually in load word reg DST. Look, this is reg DST. Where is the destination register number in case of load word instruction? It comes from bit 16 to 20. So it means REG DST must be 0. Okay. So let's write 0 here. It's not a branch instruction, so BR is 0. Okay, now in load word we are reading memory, so mem read must be 1. And let's take a look at mem to reg. What should be mem to reg? Okay, mem to reg should be 1 because we want to pass the data from the read data output of data memory. We want to let it go through to the output of the multiplexer. So mem to reg must be 1 for load word. So mem to reg must be 1 for load word. Now what about ALU op? ALU op must be 00 because we want to perform addition operation. We want the main ALU to perform addition operation. Okay, mem write must be 0 because we are not writing to memory. And now let's take a look at ALU source. Okay, what should be the value of ALU source? It should be 1. Why? Because the sign extender output will have to go through the multiplexer to the second input of main ALU, because this sign extender output is actually the offset that needs to be added to the value in RS register, and then the result is treated as an address as an address into the data memory, as an address of the data memory. Okay, so ALU source must be 1. So let's come here and let's write ALU source must be 1. And reg write, should it be 1 or 0? Yeah, it should be 1. Why? Look, this reg write has to be 1 because load word instruction is going to write something into one of the registers. So it has to be 1. Okay, very good. Now let's come here. We have store word instruction. So the opcode of store word instruction is 101011. 101011. This is the opcode of store. Oh my goodness. Store word instruction. Okay. I'm wearing a woolen gloves with my fingers coming out, and if I don't use it, I'm not able to write on my tab. But still, once in a while, the position of my fingers touches the screen and the tab goes crazy. Okay, now we want to talk about store word. In store word, reg dst, let's take a look here. What should be reg dst? Again, it should be 0 because actually here it doesn't really matter because nothing is going to get written to the register. Nothing is going to get written to the register. Okay, so let's say that we keep it 0. No, we want to use black color. Okay, it's not a branch instruction, so BR is 0. Are we reading memory? No, we are not reading memory, so this is 0. Mem to reg, let's take a look here. Mem to reg, we don't really care. Why? Because nothing is going to get written to the register. So this is kind of no op in this case. It's kind of no op in this case. We don't care. We don't care. And next comes ALU op. Of course, it is 00 because we want the main controller to perform addition. Mem write, yeah, mem write has to be 1 because store word is going to write something to the data memory. ALU source, again it's going to be 1. Reg write, it's going to be 0 because nothing is going to get written into any of the registers in the register file. Alright, so now comes the last instruction, and that is branch if equal instruction, and its opcode is 000100. 000100. Now you might be wondering from where I am getting these opcodes. These opcodes are given in your textbook, and these opcodes are also available in the MIPS green sheet, and I'm going to upload the MIPS green sheet to the I'm going to upload it to Moodle so that you are able to keep it for reference. Now in branch if equal instruction, this regdst, let's go back to black color. This regdst, this is kind of like do not care because nothing is going to get written to the register. So this is actually do not care. It's do not care for store word, it's do not care for, so we don't care what this is. It's a branch instruction, so BR signal is 1. Are we reading any memory? No, we are not reading any memory. Mem to reg, this is again do not care, we don't care. Yeah, this is going to be 0, 1 because we want main ALU to perform subtraction operation. Mem write. Are we going to write to the memory? No, we are not going to write to the memory. ALU source. This is the case where ALU source is 0, although it's a I-type instruction. Okay, and reg write, is it going to be 0 or 1? Actually, it's do not care because nothing is going to get written, but still we make it 0 because we don't want any spurious value to go into any of the registers, so we make it 0. Okay, so now we see that our truth table is complete, and this truth table completes our control portion of the processor. And if you pass on this truth table to a software tool, then it can generate the combinational circuit which implements the main controller of our MIPS, tiny MIPS processor. Now what I want you to do is I want you to study the example on page 270 of the book or 296 of the PDF. Actually, in my PDF it's 296, but just look for page 270. Page 270, the number page number 270 in the PDF, and there's an example on how to implement jump instructions. It's a beautiful example. It will tell you how the jump instructions are implemented, and with that we complete our discussion of data path and main controller. We have completed the main controller. So what I'm going to do now is I'm going to tell you to read the subsection. This is reading assignment. Oh, I'm sorry. I'm still using eraser. Reading assignment. Reading. Oh. Reading. Oops. I hate this. Reading assignment. Reading assignment is last section. Why it is last subsection of section 4.4. Why a single cycle implementation is not used today. Implementation not why a single cycle implementation is not used today. What we have discussed so far is the single cycle implementation, which means that in one clock cycle, one instruction is executed. So once an instruction is completely executed, only then the next instruction is fetched and executed. And then after that, the next instruction is fetched and executed. Okay. So this is called single cycle design. Okay. And you are going to read this section. Why single cycle implementation is not used today. And with this we come to the end of uh, our lecture, and now we will see what is pipelining. Of course, starting from the next lecture, we'll study what is pipelining and how pipelining improves performance and what are the problems that we face in pipelining and how we can solve those problems. So that's the fun part, and we will be starting it from the next lecture. So I'm going to stop here, and there we go.